Hey, this is Amber. I just thought I would walk you through what one of the weeks would look like if I'm directing and what I do when I'm directing in the class. This is mostly for my friend who is going to be directing the Challenge A next year instead of me. And I know that she's a little nervous because she's never been in Challenge, and I just want to show her one example of how this is done. But maybe it'll help some other people too. So the first thing that I always do to start off those first like 5 minutes of the Exordium is I set a timer on my phone and then we do whatever the game is. So the first like 10 weeks of Math Map, we had number knockout. And maybe I'll do a video for one of those weeks and show you what I do to make that pared down to like a 5-minute time frame. And then right now for interesting integer, it's pretty easy to keep it on a 5-minute time frame. So I would open up my phone and I'd set a timer for 5 minutes and then I'd put the number on the board. And I've just been using the numbers that they give us on the interesting integer sheet on CC Connected. You're allowed to use other numbers, but I've just been using the ones they have because they have some ideas on things to talk about, and that just makes it easier for me. So today's number, if you're using those, is 1729. And my kids are going to be like, wow, because this is such a huge number. We've been dealing with numbers like 6 and 8 and 1 and 10. So the fact that we have this large of a number, they're probably going to be all excited, and they'll probably have lots of information. So I just let the kids just start shouting out anything they can think of that relates to the number. So somebody will probably say it's odd, and somebody will probably say it's big. They almost always tell me the tally marks on this, but of course we're not going to write tally marks for this. So I might write, too big to tally, because I'm not going to write the tallies on this. So even if they try to get me to do that. The other thing is they usually will figure out the Roman numerals on this. And if you forget what the Roman numerals were, and I did for some of these big numbers, it's back in week 2 number notation on the charts is where you can find that. And I wrote it down so I wouldn't mess it up here. M, D, C, C. So that's 1,000, that's 500, 100, 100, 20, and then 29. So there is how you would write it in Roman numerals. Sometimes some of the students like to do fun things like, oh, if you took this number and flipped it on its side, it would look like a fish, or it would look like whatever. And so sometimes I try to draw that, or they see how a number looks, has a shape like something else in art. And so maybe we'll try to add that on there and draw it onto here. Maybe somebody will sum things together and say this plus this equals 1729. Maybe 1729 is a date for something in history. Maybe I'll search that actually before tomorrow and see if there's anything fun that happened in 1729 that they'll know about or ties to maybe their timeline song or something. So I'll look into that, but maybe they'll think of something too. So yeah, they could say that this could represent a date. So you just throw all the ideas that they have and let them talk for 5 minutes. And that's pretty much the extent of my Exordium. And then the next part is to go through the cover page in the booklet. And so the cover page this week is this one, Open Shapes. And so I will say, let's look at the cover. And then I usually say, so the artwork is called Peonies by Yang Shu Ping. What do you see? And so they'll start telling me how they see flowers. They might even know that they're peonies is the type of flower. I don't see any insects on here, but maybe they'll try to look really hard and see if they can find some insects. They'll say there's petals. They might count the flowers and tell me there's 3 peonies that they see. They might count the leaves. They like to do stuff like that. They might point out, I have a lot of artists in my class, so they might point out that this looks like it could be colored pencils that drew this. It could be watercolor. I don't know. Maybe one of them will know because they're better artists than I am. So they might point out some of those types of things, and I let them talk for a while. And then I try to maybe incorporate something that they talked about in the conversation page, because it seems like a good way to keep the conversation going. So I might say, how did these flowers start? Before they were this big open bloom, what did they start as? And they might point out that it's a bud. And then how does the bud change? It opens into the flower shape. And so when we think about shapes, we can think about how they're closed and then they open. And sometimes our minds have to be like that too when we're dealing with math. And even though we're kind of closed, or we maybe don't want to know something or think about something, if we open it up, we can learn something new. The next thing that I do is talk about the quote. And so the quote says, one of the endlessly alluring aspects of mathematics is that its thorniest paradoxes have a way of blooming into beautiful theories, by Philip Davis. And so I might say, how do we define paradox? Does anybody know the definition for paradox? And I can let them describe it, and they might describe it in a better way than Webster's does, but I also grabbed the dictionary definition for it. So paradox is a seemingly absurd or contradictory statement that may prove to be true. Okay, so that's what paradox means, so that we're defining our terms. And then, do you see any other terms that make you think of a flower? And they might say thorn and blooming. So those tie to a flower. And which type of flower do you usually think of when you think of a thorn? And they might say a rose. And then I'll rephrase the statement. Thorniest paradoxes blooming into beautiful theories. And so the idea, right, is that sometimes paradoxes are things that we feel like we're not understanding in math, or we explain in an odd way in math, and it works out. It can bloom into something very beautiful as we're looking at it. The other interesting thing about this statement is thorny paradoxes. So you have something thorny, and then it's almost contradictory to have blooming into beautiful. So you have two contradictory statements that are in the same line and really written in a very nice, elegant way. And what do we call that when we have that contradiction written in a nice parallel way in our sentences? And maybe somebody will realize that I'm talking about antithesis, because we just learned about that last week in exposition, but they're not always thinking about all the other strands yet at this level in challenge, so they may not figure that out, but I'll help them figure it out if they didn't, and mention how this is an example of antithesis. And then the reflection, I always read out, Lord, teach me to be generous, to serve you as you deserve, to give and not to count the cost, to fight and not to heed the wounds, to toil and not to seek for rest, to labor and not to look for any reward, save that of knowing that I do your holy will. St. Ignatius of Loyola. And so St. Ignatius is talking about the paradoxes of a believer. So we need to give without counting the cost, and we need to toil without rest sometimes, and labor without seeing the rewards. And that can be difficult for human beings. So that's why we have to lean on the spiritual dimension, or God, in order to help us get through that and do that. And usually I read it a lot slower. I'm just kind of going through this quickly for you guys, because I know you can read the cover yourself. And then any other thoughts on how the cover page ties to open shapes, and see if they have any other thoughts. Usually they don't, but that's what we open up to ask them if they have other thoughts. Then I will ask them where are we at for our domain and dimension. And so they'll look on the domain and dimension page and realize we are still on complex. We are in 3D spaces now. So we are in open shapes week 19, which is now 3-dimension. And this is our first week in 3-dimension. Very exciting. Okay, let's talk a little bit more about 3-dimension. So the next thing we do is we go to our Invention page. And I'm using my little lesson plan notes. I'm looking at them, but at the same time, I keep them on my iPad, and I work through them because I don't print out my lesson plans. It's just too much paper. Okay, so I will say, tell me everything you know about 3-dimension. And I'll just let them talk. If they want, I'll let them point out things that they're seeing on the page that they recognize or that they know, or what do they know about 3-dimension, and I just kind of let them talk through everything. And then if they're not finding a lot of things or making all the comparisons, I'll just point out a couple of things to make sure that they're seeing. And one of them is the comparison of 3D to 2D. So when we were on 2-dimension, we had two axes, right? We had X and Y, and we would talk about having infinite width and infinite height, or it might have been infinite length and then infinite height. Well, it's only two of them. So X, our X-axis, and our Y-axis. But when we get into 3rd dimension, we have infinite length, infinite width, and infinite height. So we have taken the two we had in 2D and we've added an additional that kind of like comes forward off the page, is a way to think of that. And so I have an example that maybe helps them see this. And that is the concept of the idea that when we have a second power of anything, we'll get to an area. So if the sides of your square are a length of 2 inches or whatever, and you square it, you will get to 4 inches squared, right? And we can see that when we have our shapes, our 2 by 2. And so we have our 2 by 2, and that gives us our area. So in 2 dimension, when we're squaring things, we have area. Now, if we take 2 with an exponent of 3, what is that total? The kids will say 8. And this is an example of volume. So if I look at this one, my really rough drawing that the kids might make fun of, but that's okay. You can look at just your 2, but now we are, there we go. It's like we have a block of 4 and we have another block of 4 right behind it. We have volume, so it occupies that 3-dimensional space. Okay, so that is part of our comparison, one of our 5 common topics. That's comparing 2D to 3D. And you can even go back to 1D if you want. The next thing is to define. Another one of our common topics, define an octant. And so, I'm grabbing my little octant there, sorry. Let me draw this one out again. So when we were in 2 dimension, our quadrant looked like this, right? And we have quadrant 1, quadrant 2, quadrant 3 was over here, and quadrant 4 is down here. So 2 dimension, flat rectangular plane, we just have our 2 axes, and that's what our quadrants look like. But when we move into 3 dimension, this flat plane shape becomes more like a giant cube. And we didn't have any Legos in the house. I couldn't find anything to make blocks. So I just cut out these little cube shapes in paper and just put them together. It's the last page of the lesson plan. If you want to put these together, you just need 8 of them. You tape them together, and then actually I need to go through and I'm going to label quadrant 1, quadrant 2. I'll label all the quadrants, and then we can pass this around the class and the kids can actually look at it and see it. It's a little hard to see in the paper copy. Here's the octant, but it really kind of, I think, will help them to be able to see it like this. And then you could even take something like a pencil, or my pencil might be too thick. I might need to grab some chopsticks and push it through here so you have one coming from one side, our x-axis, one coming from the top, giving you your y, and then one coming forward, which is your dimension for your z. Okay, so that's what's new in 3 dimension, is now we have this z that comes forward as well. So that is an octant, and I think it would be really great to build one of these, or if you have something that makes blocks, so that the kids can kind of see that. Then the next example question for the 5 common topics, circumstance. So how does the circumstance of the coordinate system determine how to locate points? Okay, and so how we're defining our points or finding our location. So in 2D, we're looking at our 2 axes, and then that can help us find the location of something, right? It's going to have a name that's tied to the X and the Y. When we were back in 1 dimension, oh, that marker doesn't work real well. We pretty much just have the number line. And so this can kind of give us our points and show us where we are at that point. And then when we get up to, I dropped that marker, 3 dimension, we're dealing with this, but we're coming out in space. And so we have our X, we have our Y, and then we have our Z, which is coming out. And it's kind of hard to draw that, so I'm kind of making it look like this. But that's meant to be kind of coming out of the plane. Oh, okay, so that is for rectangular coordinates, right? So the next thing to talk about are polar coordinates, and this is also still on the Invention page. So just a reminder to them, when we're talking about polar coordinates, we're just talking about a circle. And so my circle in 2-dimension looks like this. My circle in 3-dimension, I can try to represent it and draw it. Whoa, that is a really horrible sphere like that. The other thing you can do is, I meant to grab a ball. Have a ball so that you can show them the difference of that at the 3-dimension. But the first thing to point out real quick, when we're talking about a circle, when we're talking about a disc, we're talking about that outer edge and we're talking about everything inside. But a true circle, remember we did this weeks back, I don't remember when, you're just talking about that outer edge. So this 2-dimensional circle that is a closed shape, when it moves into the 3-dimension, this circle looks like this, right? Okay, so if I took this shape off the 2-dimensional plane and I put it in 3-dimension, it's open. So you have your outer edge, but then you are actually open on the inside, right? It had to be a disc in order to be closed in. And so I'm going to bring the hula hoop to class tomorrow to be able to kind of explain that a circle in 3D is actually an open shape, right? Okay, open, it goes through. Now, if I had this like as a disc, and maybe it's the bottom of, if it's part of a cylinder, so like here's a circle on the bottom of a cylinder, but then it becomes part of a closed shape because this cylinder is now closed. So I have the circle part, it's kind of more like a disc on the base, and then I have my side along here, and so this becomes a closed 3D shape that includes a circle, but really it's a cylinder. And then in terms of looking at this, what they're showing you on the Invention page, just a reminder to the kids that when we have our center point to the edge, we have our radius. When we have, when we're trying to find the angle for something along this circle, that's our theta. But over in here, we could still have our radius, right? We could still have a theta that's going some distance around this circle. But then we also have, you're not just on the flat circle moving around like a clock. You can come forward and you can go back in that ball space. You can go along the different sides. So within that ball, it's not just looking around on the flat plane, but you're kind of going forward and backwards. So that becomes a new angle, and we call that one phi. Ooh, that's a really ugly phi. There we go. So there's phi. Okay, and so that's just giving us our extra angle. It's almost like the Z, but on the polar coordinate. The next thing for common topics, relationship. So the relationship between the domain and range in 3D. I didn't put a lot of notes. I usually don't get to all 5 of these common topics. So I always write out what Dr. Gilpin puts in our tutor notes, but I don't cover each one of those. A lot of times I try to pick the things that I think are going to relate best to what they're doing on their student pages for their homework, because I want them to grasp that as they're going into those student pages. And if the kids are really getting it and we're really having a great discussion, we can move on, but usually they're just kind of like trying to grasp their heads around whatever we're going through. And then the last thing is authority. So how is the dimension for authority for the number of coordinates needed? Well, you need to know, if you're in 2D, you have 2 axes. So you have 2 coordinates that you're pulling. So if I'm finding a point here, I need theta and I need my radius. If I'm finding a point in rectangular, I need an X and a Y in order to know my location. In 3D, you're just adding that other coordinate to it. All right, so that was the Invention page. And then the next page that we go through is Memoria and arrangement. So there's some pretty crazy, scary equation stuff here at the top that I think my kids would just zone out on. So what I want to just try to express to them is what might be new in this? Because you've maybe seen things where you say like 3x plus y. We looked at that when we were talking about slopes, and we're talking about the change on stuff. But now you're seeing a new letter. What letter do you see on here? You're seeing Z. And Z, we talked about how Z is showing you have your X on your horizontal, you have your Y, which is your vertical, and your Z is showing you like how much does it come in and out of that, forward and back from that plane, towards you or away from you. So it's just showing you that dimension to it, right? The extra dimension. And so that's all I would probably talk about on the top here. Maybe mentioning how these steps, as they get into higher level math, these steps are showing the process that they would take and the order that they're going to use to take them. And that's probably all I would talk about at this point, because that's really all they need to know, and I don't want them to get overwhelmed. The other thing, to specify is that when you're looking at stuff like this, you can treat it, you can look at things and think about whether you really need to memorize something or whether you just need to put it in your Memoria. So you're understanding, trying to look at the patterns. And the way to relate that is when you had to go through essentials and you were memorizing chart A, you wanted to memorize every single part of chart A because it mattered to have that level of detail. But maybe one of the later charts like J or H, you're just looking at it and attending to it, but you're not memorizing every word on that paper because that's not as important. It's more important to try to see what the patterns are and how they relate. And that's often how these pages are. So you can kind of see, you don't want to like go through and be copying this as copy work, but just kind of see how it relates together. Like in this example, you have an image of a plane, and then if you have two planes coming together, they're going to cross and make this big mark along here, and that gives you a line because all those points are intersecting, so you end up creating a line. If you have three planes that come together, they're all going to meet up at just one little point, and so that's going to give you a point, and that's what it's talking about here. So some of this is just trying to understand how the relationships work together. All right, then the charts. Let me find where I put my charts. There we go. We don't specifically go through and talk about anything on the charts other than to just kind of see, here's that rectangular coordinate. We saw that for 2D. They're showing you example in 3D. Is it hard to draw things that are meant to represent 3D? That's a question I'd ask them. I have a lot of artists in my class, and I would say, how do you try to draw things that show 3D? And they might have some ideas on shading or perspective and how something is smaller in one place but bigger in another, and the different techniques they use in drawing. And I'll say, so just remember how hard it is to show 3D when you're talking about a 2D flat space. And sometimes it can be hard to show that in the math map too, and on your math homework. And so sometimes it can be helpful to actually get out a shape like that octant or like a sphere, a ball, to try to understand how things are relating to each other. So that's probably all I would talk about on here. Okay, I already talked about how the overlapping points make their line or make their point. Aha moment. I asked for that. Do you guys have anything you want to go through last week? They have never wanted to go through anything last week. I know most of them are still doing math map at home, but they're getting through their problems or they're asking their parents for help. And so they don't bring that to class to go through. So I offer it, but they don't usually take me up on it. I might also tell them about, don't forget about your week 29, seeing the unseen. And actually this week I have a fun example. So I didn't grab my booklet, but on my seeing the unseen, I have a little picture of a snowboarder because I was watching the X Games and somebody did a 2340. So when you are snowboarding and you go off the really steep incline and you go off the jump and you do a spin, a one-time spin, one-time rotation is going to be 360, right? 2 times rotation is going to be 720. and so on. I need to look up what the other values are. But this guy did like 6 or 6.5 or 6.25 or something. I'll have to figure out how many exactly. That made it a 2340, and apparently it was like the first time anybody's been able to spend that much in the amount of time that they had their lift before they went down and landed. So it's kind of a big deal. It's kind of a cool story, and it relates to three-dimensional space and polar coordinates. And so I just thought it's a fun example. So I'll be sharing that with them. And then the next thing that we always do, which probably takes up the last 15 to 20 minutes of class time, is to have them work through the problems on the tops of the pages for at least page 1 through 3 and sometimes page 4. And so what that looks like in actual class, they all have their copies of their booklets. Everyone in my class has their book, even if they don't all use it at home. And what I'll do is I have 7 students, so usually I'll assign 2 together to do the top of page 1, 2 to do the top of page 2, 2 together to do the top of page 3. And then if I have a student who feels comfortable working alone, and I have a couple that feel stronger in math, they might just work on it alone. Or if it's a really hard week and I don't feel like anyone can independently work, I'll put one as a group of 3 and just have them go through the tops of the 3 pages. But I like them to try to have some of that work done because it makes them feel like they can tackle it on their own when they go home and they're working on it at home. And so while they are working, so they'll actually, I'm going to have this first group do this top part and this little part right here. So usually I just do this top box. Apparently Lee feels like those top boxes are the things that are most important to cover for the week, so that's something that we focus on. But on this one, I think that's so quick that they can easily do this whole part. And so what I do while they're working together in their groups of teams or 3, I go up to the board and I divide my board. My board at campus is a lot larger, into 4. And so this is going to be page 1. And I will actually put up here their little axis so that they can, plot their stuff. So I pretty much have to just rewrite what's on here. So I would go through and do that. Space is that, which has infinite, and I'll put the blanks. So I'll pretty much mimic what's on this page up on the board. And then when they work through and answer the questions with their partner and they figure out everything, I try to tell them, okay, be sure to look at the answers, make sure you have everything right, because sometimes they come up and we realize there's a mistake, which isn't the end of the world. It's a good learning experience. But when they're done, they come up and then in a different color marker, they write in all the answers for everything. And so then when they have their time to tell about it, they can come and put in all the answers. Okay, so I would put all the problems up here, like I said, they would fill them in and then they could talk about it and explain it to their classmates. Or if we were really running short on time, I would just kind of breeze through them and ask them from their seats to just kind of give the answers real quickly and clarify if they had any problems or anything, just to make sure everybody has the right stuff going into the week in their answer keys. And then the last thing, we used to go through the catechism. That's where you're asking, where do I find my answers? How do I get more help? Like those questions. We went through that probably the first 6 weeks, but they really had that down after a while and they know where to find help. They're using it fine at home. And so I got to be honest, I usually skip that and I don't ask those. We just end up running out of time and needing to get to the next strand. So hopefully this was helpful to see what a normal week would look like for us in our class and see if there's anything useful for you to use. Thanks.